Hello, everyone. Hello, everyone, and welcome to the second session of the workshop. And I will be talking about computational spectroscopy and tools available in Q-Chem and IQMOL package to talk to molecules. So, oops, how do we? The tool to talk to molecules is called spectroscopy, which is the main research tool and arguably the only one capable to deliver very detailed information about structure of molecules and matter. In a nutshell, it works very simple. So if we analyze the light that pass through the matter, we will see that light can be absorbed at particular wavelengths. And then this pattern of light absorption or light emission is called a spectrum. So here on the top panel, you see a few historic setups like the experiment of Bunsen and Kirchhoff. That was the first application of electronic spectroscopy when they analyzed flames and looked at atomic emission. It can be very fancy using lasers and including some top-notch novel laser sources, as this aerial picture of Daisy in Hamburg shows, where there are free electron lasers, synchrotrons, and what's not. So light interacting with molecule give us a spectrum. And I think about the spectrum as a message from the molecule. The molecule tries to tell us something. It tries to talk to us. But the problem is that the message is coded. And we need a cipher to decipher it. We need a key to lead this message. And this key is given by theory, by quantum mechanics, and ultimately by quantum chemistry, which can allow us to connect these spectral shapes to find details of molecular structure and molecular orbitals and so on. So, bottom line is for every spectroscopy, we need a way to simulate the spectrum and connect spectral lines to actual atomistic details. So, what kind of spectroscopies do we have? Oh, when I signed up to give this lecture, I was panicking because there are so many different types of spectroscopies now, thousands, depending on particular setup, wavelengths of light, and so on. So here I summarized crudely just those that I thought are most commonly used. So if your favorite spectroscopy is not listed, I apologize for that. And you can see we can talk about vibrational spectroscopies. So they concern, things like hopefully some of you just were able to do it in the breakout rooms, calculating IR or Raman vibrational spectrum. There is a vibrational circular dichroism spectroscopy that allows one to get information about chiral molecules. There are a bunch of electronic spectroscopies. There are spectroscopies that probe transitions between magnetic levels and sublevels and molecules and so on. So I decided to focus on electronic spectroscopies, highlighted here, and two types of electronic spectroscopies in UV-Vis domain that probe different types of transitions between valence states, and electronic spectroscopies in X-ray domain that, by the name, using X-rays, and they deliver different type of information. So when we talk about spectroscopy, the first thing to figure out is what states are at play, because each spectroscopy probes transitions between initial and target states or final states in a molecule. In electronic spectroscopy, these are states that differ by different electron distributions. So here are a few examples. At the top panel, we see initial state, typical ground state of a molecule, and then we can use UV ionization or UV-Vis ionization spectroscopy, often abbreviated as UPS. And in this approach, we kick out an electron by light, we detect electrons, and we study their properties, and from that we get information about molecular levels. Alternatively, you can excite electron not to remove it from the molecule, and if you do it using one-photon spectroscopy, you get UV with spectrum of a molecule, and then from modeling it, you learn about molecular levels, ground and excited states of a molecule. Now you can use fancier setup. For example, you can use two-photon absorption, and the school had a lecture about two-photon spectroscopies, so I decided to include it into my talk, where you also probe transitions between ground and excited state of a molecule, but do it by absorbing two photons at once. And it's very interesting technique that delivers complementary information to UV with absorption. Now, very popular flavor of electronic spectroscopies are so-called pump probe experiments, when you can initiate a process by electronic excitation and then come with a second laser and probe dynamics of the excited state. So it's called transient spectroscopy. So in this case, our initial state is electronically excited state, which is prepared, and then transient absorption spectrum is obtained by, for example, kicking out, exciting further the molecule and probing its spectrum, as it's shown on the far right panel, or by kicking out electron from electronically excited molecule, and in this way getting information about this electronically excited molecule and its dynamics. So if you go to X-ray domain, superficially, it seems like we have similar type of spectroscopies. We can talk about X-ray absorption, XAS or Nexus absorption, where we excite electrons. We can talk about XPS, X-ray photoionization spectroscopy, when we kick electrons into the continuum. And difference from the valence spectroscopies is just that we use X-rays, and that means that we probe transitions involving core electrons, much deeper electrons in a molecule. Now, in addition to this XAS and XPS, we can also observe other processes. For example, if XPS can be accompanied by X-ray emission spectroscopy, when core ionized molecule is relaxing by emitting photon, and you can record it and get XAS spectra. We can also observe Auger and interatomic Coulomb decay processes, which also follow initial core excitation or core ionization. And in these processes, we observe ejected electrons that are kicked out from the molecule because molecule core ionized to excited state is relaxing and gives enough energy to valence electrons to go into the continuum. And there are variants of nonlinear variants of X-ray spectroscopies. For example, there is this RIX, resonance inelastic X-ray scattering, where you probe this type of transitions when you coherently excite and detect an emitted photon, and then by doing so, you can probe information about valence levels, but going through core level states. So again, it's just the tip of the iceberg. There are much more methods to spectroscopic techniques to discuss. So now what is important, and I thought I must emphasize this in this lecture, is that when we talk about electronic spectroscopy, it's true that we talk about transitions between electronic levels, but with a caveat. Since we are interested in molecules or even in materials, we cannot fully decouple electronic transitions from vibrational structure, as depicted in this picture. If we start, for example, with the ground state of the molecule and we excite molecule to some excited electronic states, very likely the geometry of electronically excited state would be different from ground state molecule, and that gives rise to so-called vibrational progression in the spectrum. So each transition will have a particular shape. So a few concepts that we need to be aware when we talk about electronically spectroscopy in molecules and are vertical transition, which is a theoretical construct not related to any experimental observables, but very popular, of course, for theorists. And this is just energy difference between ground and excited state at the geometry of the ground state. We can talk also about vertical emission if we look at the energy difference between the minimum of excited state of a molecule and ground state at this geometry. Now, more relevant to spectra are adiabatic energy differences. That's energy difference from minimum to minimum. Or even more relevant is E00. This is energy difference between zero vibrational levels in the ground and excited states. So what else do we need to have connection between theory and experiment? Well, in addition to these electronic parameters, we really want to be able to describe this shape of a transition that comes from the vibrational overlaps of the ground state vibrational function and excited state vibrational levels. They are called Frank-Condon factors. And if we can compute them, we can get this shape of a transition. So that's super important for making rigorous assignments. Now, what it means practically is that we need to deal not only with calculations of different electronic states when we model electronic spectroscopy, but also to think about these different structures and vibrational overlaps. So that makes modeling electronic spectroscopy quite involved, but fun. So, and here is a kind of a list of issues one need to think if you want to do calculation of some type of electronic spectroscopy. The first step, of course, to understand what transitions is it probing. You need to figure out what are the initial and final states in your spectroscopy. And you need, of course, to be able to compute them for your calculations to be meaningful. Now, that's just the first step. The second step is much more trickier. You need to calculate transition probability. So that's the probability that ultimately enters into macroscopic cross sections. So you need to figure out how intense this transition is. And that depends on type of spectroscopy. It could be dipole moment for some spectra, could be a more complicated expression, and so on. What else? Well, you need to decide how you deal with geometry changes. So often you need to compute optimized geometries of initial and final states. And often for proper comparison, you really want to compute vibrational structures with Frank-Condon factors. So what methods do you use? Well, it really depends on what are your initial and final states, because different quantum chemistry methods have different strengths and weaknesses in treating different types of states. You need to think about whether for your particular spectroscopy, the calculation of spectroscopic property is implemented or not, because for some spectroscopies, it may not be available, or it may be available in certain ab initio methods, but not in others. So here I have like very general overview of which methods are available in Q-Chem. And well, Q-Chem manual has 800 pages, for a reason, because there are many different methods with different strengths and weaknesses. You can consider using multi-state methods. These are my personal favorites, such these methods compute many electronic states at once, like TDDFT would be multi-state method, or equation of motion coupled cluster. Or you can consider using state-specific, we call them delta SCF approaches. They can be beneficial in some other context, when you just compute one state at a time using your best approach that you have. There are methods based on density functional theory, like DFT, with a variety of functionals and tweaks in Q-Chem, or you can use wave function-based methods, such as coupled cluster theory or ADC methods. So when we talk about spectroscopy calculations, some types of calculations are built in Q-Chem. So when you run Q-Chem calculations through IQmol, you will get all necessary results and your final spectrum even. Now, some calculations are more involved and require post-processing. And for that, we also have a number of tools. For example, we have this Easy Spectra package that can compute various types of spectroscopy as a post-processing of your calculation. And also, last but not least, if we are going back to this idea that we want to actually learn from molecule its fine details, the ability to interpret your electronic structure calculations and your spectrum in terms of molecular orbital picture is very important. And for that, we have this a number of tools, and in particular, wave function analysis tools, which I think are just very nice set of tools to understand the nature of your spectroscopic transitions. Okay, so this is a diagram that highlights my favorite family of methods, equation of motion coupled cluster methods. Again, it's not the only thing which is available in Q-Chem, but because it's a short workshop, I will use this method as an example of different calculations of spectroscopic quantities. And in this method, we describe ground state of a molecule by coupled cluster wave function, and then excited states are described as eigenproblem, as diagonalization of this similarity transformed Hamiltonian. And then you have a ability in these methods to compute states of different nature. For example, if you start with the typical ground state of a molecule, you can then calculate all sorts of excited states, including core excited states. You can start with this ground state of a molecule and then compute all sorts of ionized states, including core ionized states, and that would be appropriate for other spectroscopies. Can do electron attached states, double ionized states, so many different variants. What is nice about this family of methods is that you have built-in balance, because these different types of states are described by using the same effective Hamiltonian, which is great for spectroscopy. And it also convenient that you calculate different states in a single step. So you can really get a big picture from a single calculation. All right, now maybe I should say a few words about extension of equation of motion to core level states. As I said superficially, if you think about exciting or ionizing core electrons, it sounds like just using different energy in calculations. However, there are problems if you try to just apply standard method to do this. And the problem arises from the fact that when you remove or excite core electron, you create extremely highly excited states, like at 300, 400, 600 electron volts. And these states is metastable, it can decay. And these states lie way above many other states below it, and that creates a mess. So practical solution to this problem is to use so-called core valence separation, in which core level and valence excitations are decoupled by pruning your excited state configurations. And this method, again, this idea is very old, dates from 1980s, and that really works great for calculating of core level state. And this idea is used in several variants in our extension of equation of motion to core level states, in ADC method, also extended to core level states, and even in TDDFT, where it's traditionally called restricted excitation space. Okay, so last topic, vibronic spectra. As I said, we want often to calculate vibrational progression for electronic transitions, for example, for ionization or TDDFT, or for ionization or excitation. And Q-Chem offers a set of tools for that. We have today, I will show you an example of built-in calculations that you can perform with IQmol and get your vibrational spectrum, like the one shown here. And for that, you can only run Q-Chem and IQmol. Now, there is also a tool available to everyone as a standalone post-processing package called EasyFCF. And for that, you need to run first necessary Q-Chem calculations and then run the software to calculate spectra. So the advantage of this is that you can combine it with many different methods, and it has also additional nice features. So, all right, I compiled here a few suggestions of further reading related to different types of modeling electronic spectroscopy, and also further listening and viewing, because this is not the first time we talk about spectroscopy. There are a number of webinars from Q-Chem and also materials from the previous winter school. So with that, let me go to the exercises. So what I will do, I will explain what are the 4 exercises that we prepared. Now, we prepared 4 exercises. I do not think you have enough time to do 4 of them, but I thought that people can choose whatever they find most interesting for their research, and they do not need to be done in any particular order. So pick your favorite one and start from it. So the first 2 exercises are actually the same as we gave last year. So if you are returning participant, you already done them, and they are related to calculating excited states like in UV spectroscopy, or core excited or core ionized states like in X-ray adsorption spectroscopy. So 2 new exercises. One is two-photon spectroscopy calculation using equation of motion for excitation energies. And the next second one is Vibronic calculation using built-in Q-Chem capabilities. So how can you get Frank Condon spectrum by just running Q-Chem with IQMol? So all the exercises are in the Google Drive, to which you have already link. So here are just a very brief description of what you will be doing. If you do excited state calculation with equation of motion coupled clusters, you will need to select in IQMol proper method, and then you need to tell what type of states you wish to compute, and you need to tell whether you want singlets, triplets, both of them, and how many in each symmetry rep. So if you want to compute transition properties such as oscillator strengths and transition dipole moments, you need to say it explicitly. In the example we give, we calculate oscillator strengths for transitions from the ground state to excited states. But you can also set calculations by calculating transitions between different excited states, as one need to do in the transient adsorption spectroscopy, for example. So this option is also exist. So the second example is related to core level states, and it refers to calculating of ionized states. So that would be CVS UM-IP calculation, and there are a few details here. Now I want to say that we discovered a glitch about oxygen H calculation, so the TAs can explain what it is. So just do calculations of carbon H for now. So it's related to some interaction between IQMol and Q-Chem. So two-photon example is shown here. Again, you use here CVS UMEE calculations, but you specifically tell Q-Chem that you want to calculate two-photon transition probability, two-photon cross sections. So that will require a few more additional calculations because of this, how theory is working. And the last calculation, in the last example, you will be doing TD-DFT calculation of Vibronic S0 to S2 transition, actually not S0 to S1, I will need to correct it, in Q-Chem. And yeah, so that's it. So have fun. So please go to breakout rooms, select whatever exercise you want to start from. And by the end of the session, TAs will present results of all 4 exercises. Thank you.
UMEE jobs. So what we can do after we set up correctly the job is just parsing the important information from the output file. So first we can record the excitation energy for each excited state. So we can see it here on the left. We can see excitation energy in electron volt, and we can also see the relevant molecular orbitals that are involved in the transition. At the same time, we can get the transition properties. So again, Q-Chem prints excitation energies in EV, but also what is important here is to record the strength of the transition, so the oscillator strength over here, which connects experimentally with the height of the peak. So it in regular absorption spectrum, so it tells you how likely a transition is. And we can do this job for all our excited states, and we can report them in this table, so we can see all singlet and triplet states with their related symmetries. And we can see here that all the triplet states have oscillator strength of 0, and that's normal because transition from singlet to true triplet state are spin forbidden. We can also have a look at what these electronic transitions look like by plotting the molecular orbitals. So in principle, we could plot all the molecular orbitals that are listed over here, but it is actually better to print the natural transition orbitals, which are a different mixing of the molecular orbitals that we had before in a more compact way that make more sense and allows to represent the transition with fewer orbitals. So the transition is represented in terms of pairs of hole and electron orbitals. So the hole orbitals are on the left and the electron orbitals is on the right. And the meaning of this orbital picture, it basically tells you where the electron was and where the electron went upon excitation. This is a very rough description. So this is very useful for characterizing transitions so that we can distinguish between pi-pi star transitions or n-pi star transition. And the weight of each NTO pair that is relevant for your transition is given by these sigma values, which just a number that comes from a singular value decomposition. But that's you can read more in the Q-Chem manual. And that's it for this exercise.
Hello, so I will be explaining the results of CVS EOM calculations. So first I will explain EOM IP, then EOM EE for core level calculations. So for EOM IP, the thing to look at is the excitation energy, which actually shows the amount of energy that's required to ionize an electron from a core orbital. So here for the carbon edge, we get the excitation energy. Also here, we get the orbitals that are involved in a particular transition. Similarly, in the case of CVS EOM EE, that is when an electron is excited from a core orbital S orbital of carbon to an virtual orbital. Here we can see that more than one configuration is involved in the transition. So here you can see the multi-configurational character of the wave function as well. And similarly, as Goran had explained, for a CVS EOM EE calculation, we can calculate the transition properties. From there, you get the oscillator strength and dipole moment involved in a transition. And the same calculations can be done for oxygen edge as well. So here you can see that for carbon edge and oxygen edge, the energies, ionization energy and excitation energy are substantially different. So this is an feature of core level spectroscopy because core orbitals are very compact and localized. So it is very easy to distinguish a carbon core from an oxygen core. And for EOM IP calculations, Dyson orbitals would show us a metric of such ionization. So here we can see that for CH calculation, the Dyson orbital is localized on the carbon orbital, and it's a 1s orbital of carbon. Same for the oxygen edge. And for CVS EOM EE, you can also do NTO analysis to see the electron hole pair, that is to see where the electron is getting the orbital from which electron is getting excited and to see where it is going. So these are the results for CVS, EOM, IP, and EE.
Lani, you're muted.
Hello, I can't unmute. Am I, can you hear me?
We can hear you
yes.
now, yeah.
Okay. Here I'm going to present the results for EOM-EE for the 2PA of butadiene. If you run the calculation successfully, you will find these 4 excited states, which are from the AG symmetry block. If you just run EOM-EE with 1 photon, you will see that these excited states are dark in nature, but with 2PA, that is with 2 photon, we will see that these are bright transitions. And here I am listing the excitation energies for all of these states. Here, these are the molecular orbitals which are involved in these transitions. Here you can see the symmetry of the orbitals and the numbers. And from here you can compare the pictures of these orbitals. And this quantity sigma parallel, it shows us the strength of the transition. And you can see the brightest one here is the 4Ag state. I think, yeah, that's it.
All right, I think I'll go next.
Yeah.
All right, so I hope by now you'll be able to see my screen. And so this is the exercise which Dr. Krylov has introduced, where the electronic transition formaldehyde was resolved by its vibrational progression. And as Dr. Krylov has mentioned, that's the transition from the ground to the second excited state. And it's the result of it is basically just one file that's called ABS spectra, and that file is separate from the Q-Chem output. To show the spectrum that was calculated, it's enough to plot what's the data in this file. The first column contains the wave number, which is the position of different features in the spectrum. And in the last column appears the intensity of these different features. And what this spectrum presents is that the electronic transition can be resolved by seeing individual vibrational states in the electronic states. And that's all from me. Thank you.